So for part 1 of this assignment, I did the 8 puzzle solver. Firstly, I have a hash table, which holds the created keys of the boards, as well as the keys of the parent board. I then have a list of boards called closed boards, which are the boards that have been visited. I also have a priority queue using a priority queue package, which holds all of the open boards as well as their F-score. And the F-score is used as the priority number. I have a board for the goal board, a board for the start board, and a board for the current board. And then I have moves, which I initialize to 1, because the end board I count as a move. I then have a boolean here for if the board was able to be solved. It's initialized to true, and it becomes false in a while loop later on if all of the open board lists items have been visited and it hasn't been solved. Inside of the main function, I have 2 2D integer arrays, one for the goal configuration and one for the start configuration. I made sure for the purposes of this that the start configuration was one that could be solved. The goal board is initialized to be a new board using the goal int array that was created above, and then I display the goal board. I do the same thing with the start board. The second parameter to the new board constructor is the goal board, and I use the goal board created above for that. I do have the option here of doing a random start board. It is currently commented out. I will show that later. I then display the start board and set the goal board of the start board equal to the goal board. That is only for when the... Actually, I don't need that. I'm taking it out. I then add the start board key to the hash table with null for the parent hash. I add the start board to the closed boards list because it's been visited. And then I add the start board and its F-score to the queue. I then make the current board a copy of the start board. So before we get into this while loop, I'm going to scroll down and show the board class. So the board class has some variables here. One is for the size, which is initialized to 3. One for a 2D integer array that holds the board information. I then have a string for the key to be used in the hash tables, as well as integers for the F-score and the G-score. And then I also have a board for the goal board, which is used to calculate the H-score later on. The first constructor I have here takes in a 2D integer array for the initial configuration of it, as well as a board for the goal, which is initialized to null because on the goal board you don't need a goal board. So inside of it I set the configuration to the provided one, I set the goal board to the provided goal board, I use the board key function to get the key for it, and then the F-score function to get the F-score for it. The second constructor I have is for when I'm making the random start configuration. This one just takes in a goal board, and then it uses initialized board to get the random values. It sets the goal board equal to the provided goal board, and it gets the key with the board key function and the F-score with the F-score function. Here's the function I created to display the board to the user. So first, just for formatting, I have a line there with a bunch of stars, asterisks. After each loop of the outer loop, I do a right line to display the new row. And then in the inner loop, if the value at the position is 0, that's the blank tile, so I only display the blank. Otherwise, I'll display the value with spaces around it. At the end, I just add 2 extra lines for formatting. Here's the board key function, which returns a string for the key to be used in the hash table. First, I create an empty string called k. I loop through all the items in the board array using the size, and for each item, I add to k the value of the tile at that location. And after it's all done looping, I return the string. This allows me to use hash keys that are unique to each board without duplicating it if a separate instance of the same board configuration is created. I then have a function called findLocation, which returns a tuple with the tile location within the board of the number that is provided. So first I create a tuple called t that is initialized as null. I then loop through all of the items in the board array, and if the value at that position is equal to the requested value, the tuple t is the new tuple with the values I and j as the position, and then I return t so I can stop looping through. At the end, I return t. It should never get to that point to where it returns a null t, because if I'm asking for a num value, it will be within the board. Scrolling down, I have functions that return bools for up, down, left, and right. They all essentially do the same thing. I use find location 0 to determine where the blank space is. If the y value of the location of the blank space -1 is greater than or equal to 0, that means it's allowed to move up without being out of range. So I return true. Otherwise, it cannot be, so I return false. I do this for down as well, except for I do the y value +1 and make sure that it is less than or equal to the size -1 to make sure it isn't out of range. I do this for left as well, except I check the x position -1. It has to be greater than or equal to 0. And I do the same for moving right. If the x location +1 is less than or equal to size -1, it's within range, so it can be moved right. I then have the functions to actually move the blank tile up, down, left, and right. Firstly, within each of these, I get an index of the location of the blank tile using a tuple. In this case, I'm trying to get the value of the board item that is above the blank space. So I get the y value of the 0, subtract 1 from it, and the regular x value. And I use those to get the value at that location. I then set that location's value equal to 0, and I set the value where the 0 was equal to the number that it used to be. I then get a new key for this board and return the board. I do the same thing for down, except for I get the location below the blank tile location. Do the same thing for left, except I get the location to the left of the blank tile location. And same thing for right, except I get the value for the right location. Further down, I have the function to get the f-score. If the key for this board is the goal key, I return 0 because the f-score is 0. I then initialize the h-score to start at 0. And then I loop through all of the items in the board's int array using the size. For the difference, I get the location at I, and I do its y value minus the goal board's y value there, and I add it to this board's x value at that location minus the goal board's x value at that location. And then I add that difference to the h-score. After looping through all of them and adding them to the h-score, I return the h-score plus the g-score. I then have a function to copy the current board, so I create a new 2D int array called new board using the size. I loop through all of the items in the array. I set the new board's value at that location equal to the current board's value at that location. After filling out that int array, I create a new board using the new board and using this current goal board as the goal board. I then find the board key and I return the new board. This is my function to initialize a board with random values. First, I create a list of integers called nums, and then I create a random to get random numbers. And then I have an int for the current number, which is not yet initialized, and I have a boolean for if it's done getting all the numbers I need, which is initialized false. Then I have a while loop that continues while it's not done, and I set the current number equal to a random number between 0 and 8. If the number array does not contain the current number, I add it to the list. If the number array now has a size of 9, I've gotten all the numbers I need, and I set done to true. After getting all the numbers I need in the list, I set the index to 0, and I loop through all the items in the array using the size. I set the item at that board position to have the value at the index of the numbered list, and then I increase the index number. This way it uses all the numbers from the list while creating a random configuration. Going back up to the main program, I have a while loop that continues as long as the current board's key is not the goal board's key. First, I have an if statement that checks if the open board list is equal to 0, but the goal hasn't been found. I say that this could not be solved, and I set could complete the false, and I break out of the while loop. This should only ever happen with the random configurations because some 8 puzzles are not solvable. If the queue count is not 0, it moves on and it gets the available boards. Scrolling down to that function, I set the current board equal to the first board in the queue, and then I dequeue the item from the board, and then I add the current board to the closed boards list, meaning it's been visited. I then check if the board's blank tile can be moved up, down, left, and right. If it can, I create a new board for it by copying the current board and calling move up, down, left, or right on that board. And then I call add board using that board as my parameter. Scrolling down to add board, it checks that the hash table does not already contain the key of the board. If it doesn't, it means that this has been found for the first time and it needs to be added to the hash table. So I add it using the board's key and the parent as the current board's key. I then add it to the open board queue using the board and its F-score. Scrolling back up, the while loop will repeat this until the current board is the goal board. After that, if it was able to complete, which it should unless it's a random configuration and it's an unsolvable 8 puzzle, it displays the final path, calling display path. Display path starts with a string called path, which is equal to the goal board's key. I then create a list of the final boards that were actually used. I then have a while loop that continues as long as the hash table has a value corresponding to the path key provided. As long as it does, it adds the board with this key to the final list using the getBoardFromKey function, which I will scroll down to in a second. And then after that, it sets a new value for the path, which is the value of hash path, which is the parent's key. This is essentially tracing from the final configuration, the goal board, back to the start one. Down here in getBoardFromKey, it takes in a string k, which is a key, and it returns the board that key belongs to. So it loops through all the boards in the closed board list, meaning the boards that were visited. If the key of that board is equal to the provided key, it returns that board. If the key wasn't found, it returns null, but this should never happen. Back up to displaying the path. After it adds all of those to the final list, it displays the start board, and it loops through all of the boards in the final list, and it loops through all of the boards in the final list going backwards, starting from the end going to the beginning. Each time it goes through this loop, I increase moves, which is the number of items in the final path from the start board to the end board. At the end, I display the goal board, and here's the code running. As you can see, it took it 33 moves for this one. It shows the goal board and the start board, and then the final path from the start board to the goal board. So here it moves right, up, right, down, and so on, until we get to the final board. So for part 2 of assignment 2, I decided to do pathfinding for the real world application. I imagine this could be used in video games to find the shortest path from a enemy to the player, or from an AI that's like racing the player to its destination, something like that. So to start with, I have lists for the open locations that have been discovered but haven't been visited, and a list for the closed locations that were discovered and visited, and a list for the final path that has the final locations visited for the shortest path. I also have a location here for the target location, and then a location for the starting location, and then a 2D array of characters for the world layout, and then a size, which I currently have as 8. Scrolling down to the bottom here, I have the class for the location. This just has ints for the X and Y location in the world, as well as the location's F-score, G-score, and H-score, and also the parent location. So going back up, the program starts out initializing the open location, closed location list, and setting the current location to null, because there's not one. And then I also initialize the final path list. I also have the G-score, which starts out as 0 because we haven't moved yet, and that'll increase every time there is a movement made. I then initialize the 2D array for the world. S is the letter for the starting, E is for the ending, the O's are open spaces that can be moved to, and the X's are spaces that are blocked that it will have to go around. I then loop through the world array using the size variable, and if the item at that location is equal to S, I set that location for the starting position, and if it's E, I set that location for the target position. Then I add the starting location to the list of open locations that haven't been visited. Then I have a while loop that continues as long as there are open locations and as long as the target hasn't been visited. I then have an int to hold the lowest F-score using the find lowest function. The find lowest function sets an initial minimum number equal to the first item's F-score in the open locations list. Then I loop through all of the locations in the open location list, and if one of their F-scores is lower than the current minimum, their F-score is the new minimum. And then at the end I return the minimum. I then set the current location equal to the index of the first instance of the lowest F-score, which I use the find first instance function for, which is down here. This takes in the F-score you're looking for, and it loops through all the locations in the open location list, and when it finds the first location with the requested F-score, it'll return that location. Otherwise, it returns -1, which should never happen. Coming back up, now that the current location has been set, you can add it to the closed locations list because it has now been visited. Then I use the current location's X and Y positions, and at that position in the world, I set it equal to just a period to show the location that has been visited. And then I display the world again. I then remove the current location from the open locations list since it has now been visited. At this point, I use the enclosed list function to check if the target locations are in the closed list, and if they are, I break out of the while loop since it's been visited. Scrolling down, enclosed list returns a bool. It loops through all of the locations in the closed list, and if one of them's X and Y is equal to the X and Y that was provided, it returns true to say that that item is in the closed list. Otherwise, it'll return false to say it wasn't found in the list. I then create a new list of possible locations, and I set it equal to the value returned from the getPossibleLocations function. In this, I provide the current location and the world configuration. Scrolling down to getPossibleLocations, this returns a list of locations. First, I initialize a list of possible locations and a list of final locations. The possible locations list is for all possible movements from the current position, including the blocked locations. The final locations list is narrowed down to ones that do not include blocked locations or locations that have already been visited. So first, I check that the Y location -1 is greater than or equal to 0, which means that it can be moved up, and I add that location to the possible locations list. I do the same thing for the down location, checking that Y plus 1 is less than or equal to size -1 to make sure it's within the bounds. I do the same thing for moving left. X -1 checks if it can move left. It can if it's greater than or equal to 0. I do the same thing for moving right. X plus 1 has to be less than or equal to size -1 in order for it to be able to move right. After adding all of those to the list, I loop through all the locations in the possible locations list, and if it's open or if it's the end tile, it can be added to the list. Otherwise, it's not added to the final locations list. And then at the end, I finally return the final location list. After getting the possible locations, I increase the G-score since we've moved once. I then loop through the list of possible locations. If the location is not in the closed list, which means it hadn't been visited, I then check that it isn't in the open list, meaning that this is the first time this has been discovered. I do this using the inOpenList function. Scrolling down to inOpenList, it takes an X and a Y integer. It loops through all the locations in the open location list. If one of them has the same X and Y values as provided, it'll return true, saying that the item has been discovered before. It'll return false, saying that it has not been. Going back up, if it is not in the closed list and if it is not in the open list, I set the location's G-score and calculate its H-score using the H-score function, which takes in the X and Y location as well as the target X and Y location. I'll scroll down to that in a second. I also set its F-score by doing the G-score plus the H-score, and then I set the parent's location equal to the current location. And then I add this location to the open locations list. Scrolling down, I calculate the H-score by taking the absolute value of the target X minus the position's X, and adding it to the absolute value of the target Y minus the position's Y. And then I return that H-score. After this while loop that finds all the locations, I have another while loop that loops while there is a current location. If there is one, I add it to the final path, and then I set the current location equal to the current location's parent. This is going to trace it back from the end to the beginning, adding each of them to the final path list. After that, I loop through the final path list, going backwards. I set the current location equal to the index of I in the final path. I then set that location's value to be P for path in the world, and then I display the world, and then I sleep for a second. This way the user can watch the P go through for the path. Afterwards, I do a write line saying that it's complete, and I do a read line so the window will stay open. I also have the display world function right here that was called a few times throughout the code. This loops through all of the items using the size variable, and it formats the display of the world to the console. So it has a line break between rows, and then it has a space around the value of each item in the world, and then it has another write line after. So here is the running code.